Assalamu alaikum. That is lecture 2 for current week, whose title is Microprocessor Programming and Interfacing, whose code is CS430. Before we start today's lecture, we have to take quick review of the previous lecture. In previous lecture, we have covered instructions belonging to arithmetic and logic group of instructions. We have covered ASCII arithmetic instructions for unpacked BCD form. Then we covered rotate instructions, shift instructions, and then we discussed conversion instructions from byte to word and word to double word. In this lecture, we are going to cover transfer of control group of instructions. So first instruction for this group is jump instructions. So there are two types of jumps: unconditional jumps and conditional jumps. Mnemonic for unconditional jump is JMP, and there are three subtypes. Unconditional jump may be of short type, near type, or far type. So for short jump, there is a limit for jump. You may go from the current location, you may go forward plus 7f locations, or you may go backward in the back direction minus 80h locations from the current location. So that is the limit for short jump. And beyond this border of 7f in the forward direction and backward minus 80h, if you go beyond that limit, then your jump will be of near type if you are not changing the code segment number. In far jump, whole 1 megabyte real memory will be in the reach of jump. You may jump anywhere within the 1 megabyte real memory. And conditional jump will be of only short type. So limited space is available for short jump instructions. From the current location you may go forward plus 7f locations, or you may go backward minus 80 locations. Now we have to discuss unconditional jump, that is JMP. Standard format for JMP is given JMP operand. From that operand, new value for IP and CS will be loaded, and different possibilities for operand are given. That operand may be a short label or a near label or a far label, or you may use a 16-bit register or a pointer within memory, near pointer or far pointer. So we are having some examples here. First example is JMP 180. So that is written at offset 100 within code segment. So we have to calculate displacement, and that is, if we consider this jump as a short jump, that will be of 2 bytes. So next instruction will be at offset 102, that will be current IP value. So we have to subtract 180 minus, we have to perform subtraction 180 minus 102. So displacement value is 7e, that is within the limit. The maximum limit is 7f, so 7e is lesser than 7f. So that instruction may be stored as short jump. So there will be 2 bytes. EB is the opcode for short jump, and 7e is the displacement value. When this jump instruction will be executed, current IP, that is 102, will be added with 7e, and you will be having a new IP, that is 180, and jump will occur. Now we are going to discuss second instruction, JMP 3040 hex, that is written at 102 offset. If we calculate the displacement, so we found that displacement is of 2 bytes, and the value for displacement will be 3040 minus 105, as this jump is of near type, so that will be stored in 3 bytes, written at 102. Next instruction address will be 105, so we have subtracted 105 from 3040. to calculate the displacement. So displacement will be 2f3b. So opcode for near type of jump is E9, and we have to store displacement in 2 bytes. Lower byte for displacement is 3b, higher byte for displacement is 2f. Third example is for far label. So we are having JMP 4500 colon 0430. So first address mentioned here is the new value for CS, and second operand mentioned is the new value for IP. So 0430 is loaded in IP after execution of instruction, and 4500 is loaded in CS after execution of the jump instruction. And that jump instruction will be stored in 5 bytes. E is the opcode for fast jump. Then we have to store lower byte for IP, that is 30, higher byte for IP, that is 04, then low byte for CS, that is 00, and higher byte for CS, that is 45. So that instruction will be stored in 5 bytes in memory. Now we have to discuss jump AX. Jump AX is written at 10A offset within code segment. So machine code is FFE0. When this jump instruction will be executed, new value for IP will be loaded from AX register and jump will occur. Now second last jump near pointer within square bracket VX. So new value for IP is to be loaded from memory present at offset address BX within data segment. Machine code is given. FF27 is the machine code for this jump. Last instruction is jump far pointer within square bracket BP plus 4. So as the far pointer is given, so both IP and CS are to be loaded from the memory address. So from BP plus 4 within stack segment, a word will be coming from memory and that will be stored in IP. And another word will be fetched, will be read from memory from offset BP plus 6 within a stack segment, and that word will be stored in code segment register. Machine code for this instruction will be FF is the opcode, and 6E and 04 is the description for this instruction. We are not going into the detail.
Now we have to discuss conditional jump instruction. General format for conditional jump is the mnemonic of conditional jump, J condition, then a label of short type, and as this instruction is of short type, that will be stored in 2 bytes. First byte for opcode. Opcode will be varying depending upon the condition. So first byte is 0111, and there are 4 bits for C, and these C bits are showing which conditional jump is to be executed. And in second byte you will be having an 8-bit displacement. In case of condition becomes true, IPC will be added with this 8-bit displacement, and you will be having a new IP, or you may say that if the condition is true, jump will be executed, and that jump may be in the range of plus 7fh in the forward direction, and in the reverse direction minus 80h. So otherwise, if the condition becomes false, then no jump will be executed, no change in the program flow, or that may be said that the next instruction in the flow of the program will be fetched and executed. All the status flags except auxiliary carry flag are used to test the condition before executing the jump. So all the different jumps are available. Most of the jumps are dependent upon the only one flag bit, uh, and some others are dependent upon the more than one flag logic levels. So there are some mnemonic of jumps having words greater than and lesser than. So those jumps are related to signed numbers, and those jumps are called sign number jumps. And for condition, you will be checking zero flag, sign flag, and overflow flag before executing jump. Some other instructions, conditional jump instructions, are having above and below words within the name of the jump. So those jumps are related to unsigned numbers, and in case of unsigned number jumps, zero flag and conditional carry flag will be checked for the condition, and jump will be executed after the checking. So that is the table for conditional jump, different type of conditional jumps. So in the first column you are having the code CCCC 4-bit code. So to the power 4, 16 different conditional jumps are possible, and mnemonics are listed in the second column. GO and description of these mnemonics are given in the last column. So GO means jump if overflow, JNO means jump if no overflow. Uh, then you are having JB slash JNAE. JB means jump if below, or otherwise jump if not above and equal. So two mnemonics for the same jump are available. In fourth entry you are having JAE slash JNB, that means jump above or equal. JNB means jump if not no, jump if not below. Then you are having jump if equal or jump if zero. Then you are having JNE slash JNZ, jump if not equal, jump if not zero. The operation is the same for both. JBE slash JNA, jump if below or equal, jump if not above. Operation are the same for both. JA slash JNBE, that is the mnemonic for jump if above or jump if not below or equal. JS means jump if sign, JNS means jump if not sign, JP means jump if parity bit, jump if parity slash JPE, jump if parity even, JNP jump if no parity slash JPO, jump if parity odd. Then you are having JL slash JNGE, jump if less slash JNGE means jump if not greater or equal. JGE, jump if greater or equal slash JNL, jump if not less. JLE means jump if less or equal. JNG means jump if not greater. JG, jump if greater slash JNLE, jump if not less or equal. So these are the different conditional jumps, and flag listing are given on the flag checking conditions are given in the third column of this table. So most of the jumps are dependent upon the logic level of single flag. Some other instructions are dependent upon the two flags. As for JNA or JBE, you are having two flags. Carry flag should be one, or zero flag should be one. Or means any one condition will be satisfying the condition, and jump will occur. In case of JA and JNB, condition is carry flag is 0 and zero flag is 0. Both conditions are to be satisfied for execution of jump. Otherwise, if any one of the conditions are not satisfied, then this jump will not occur. In case of JL, you are having two flags, sign flag not equal to overflow flag. So if sign flag is 1 and overflow is 1, this jump will not be executed. If sign flag is 1 and overflow is 0, then the condition is satisfied uh, for this jump JL and JNGE. Same Now you may see JLE, JLE, or JNG. Sign flag is not equal to overflow flag, or zero flag equal to 1. Any one of these conditions are to be satisfied for execution of JLE condition, a JLE jump. In case of JG, sign flag should be equivalent to overflow flag and zero flag should be 0. Both conditions are to be satisfied for execution of jump for or satisfying the conditional jump condition. So in now we are having some examples for conditional jump. We have performed an arithmetic operation. We have moved 9000 hex in AX, then we have subtracted 4000 from AX register by using compare instruction. So result will not be stored, but condition will be generated. So carry flag is 0 after this subtraction. Parity flag is 1. Auxiliary carry flag is 0. Zero flag is 0. Sign flag is 0, and overflow flag is 0. Now first instruction is JNE, jump if not equal, and you have to jump to 130 location. So if you calculate the displacement, so displacement value will be 130 minus 102, and you are having 2e displacement. So that is within 7f limit. So machine code for this instruction will be 75 space second byte 2e. So there are 2 bytes for this machine code of this instruction. Operation of this instruction is if zero flag is equivalent to 0, jump to 130, and here the condition is satisfied as zero flag is having logic 0. So for our example, condition for JNE instruction is satisfied, so jump will occur. Now we are going to discuss second instruction, JA 150, that is written at 102 offset. So now we have to calculate the displacement. Displacement is 150 minus 104, so that will be 4c, that is within the limit of 7f. So this jump will be stored in memory. 77 is the opcode for JA instruction, and in the next byte you will be having displacement 4c. And for jump above instruction, two conditions are to be satisfied. Carry flag should must be having logic 0, or and zero flag must be 0. So you may see here that both conditions are satisfied, so jump will occur. Condition is true for this JA instruction. And you may see that if you see the calculation, 9000 is present within AX, and you have subtracted that 4000 from 9000 to generate the condition. So this JA instruction is checking that 9000 is above 4000 or not. So as you may see, if you consider both numbers as unsigned numbers, so 9000 is greater than 4000, so jump will occur. Condition is true. Now we are going to discuss next instruction, JG, jump if greater 150. So here if you see value present within AX and the value with which you are comparing AX, 9000 and 4000. So 9000 is a negative number and 4000 is a positive number. So if you test the condition for JG, 9000 greater than 4000, that is not true, because 9000 is a negative number and 4000 is a positive number, and negative number may not be greater than a positive number. So condition for JG is failed. And if you see the condition with respect to the flags. Sign flag for JG conditions are if sign flag is equivalent to overflow flag, and second condition is zero flag is zero, jump will be occurring, otherwise condition is false. So here sign flag is having logic 0 while overflow flag is having logic 1. So first condition for JG is not satisfied here, but zero flag is having 0. But first condition SF sign flag equivalent to overflow flag is not satisfied. That's why condition is false for this instruction. And machine code for JG instruction will be 7F, that is the opcode, and displacement will be 4C, as you have to 4A is the displacement, as you have to subtract 106 from 150 to calculate the displacement. Now we are having JB instruction, jump if below 180. So condition for JB is carry flag must be having logic 1 for true condition. So here you may see that carry flag is having logic 0. So condition is false for this JB instruction. Opcode for JB is 7F 72, and displacement for JB will be calculated by subtracting 108 from 180. So that is the displacement 78. Now we are having JL instruction 180, JL 180. Condition for JL is if sign flag not equal to overflow flag, jump will occur. So sign flag is having logic 0, overflow flag is having 1, so condition is satisfied with respect to the flags. If you see both numbers are unsigned, 9000 and 4000 as unsigned numbers, JB is checking 9000 less than 4000 and considering both numbers as unsigned numbers, so that is false. 9000 is greater than 4000 if you see both numbers as unsigned numbers. But in case of JL, you have to check now 9000 as signed number is lesser than 4000 as signed number. So 9000 is a negative number and 4000 is a positive number. So if you see both numbers as signed numbers, condition is true. So that is the case here. So opcode for JL instruction is 7C, and displacement is 180 minus 10A 76. So that is within 7F. Uh, so that is okay. 2 bytes will be stored in machine in memory. Now we are having last instruction JS 190. If sign flag is having logic 1, then jump will occur, otherwise jump will not occur. But if you see the displacement value 190 minus 10C, so your displacement is 84. So the 84 is greater than 7F. So that is your destination IP or new IP value is crossing the limit for forward displacement, that is 7F. So that instruction may not be stored in memory. So assembler will be generating error and is specifying that the new IP value is not within the limit. So that instruction may not be stored in memory. So that will not be converted into machine language. Now we are going to discuss subroutine handling instructions. For calling a subroutine, we use call instruction, and for coming back from the subroutine, we use return instruction. Mnemonic is RET. So we have to discuss call here. Standard format for call instruction is call operand. In response of call instruction, current location of program will be stored on top of the stack by pushing CS and IP values on top of the stack. Then new values for IP and CS are loaded by using the operand. And different operations of operand are given here. That may be a near label or a far label or a 16-bit register or a memory near pointer within memory or a far pointer for memory. If you see the difference between jump and call instruction, in case of jump instruction, you were not saving the current location and you were loading the new values for IP and CS. But here in call instruction, you are saving the current location on top of the stack, and then you are loading new values for IP and CS. And second difference is that there is no short label present in case of call instruction, but in case of jump instruction you are having short label, near label. So there is no condition for displacement is to be checked for storing instruction as short jump or near jump, but all the call instructions will be stored as near calls if code segment is not changing. So we are having some examples here. First call instruction, call 180 is written at offset 100 within code segment. So if you calculate the displacement, you have to use current IP value 103, as the first instruction will be of 3 bytes. So current IP value will be 103, and destination IP or new IP value is 180. So displacement will be 180 minus 103, 007D hex. So that is the value for displacement. So instruction is stored in memory. Machine code is given in the last column of the table. E8 is the opcode for near call, and now you have to store displacement in 2 bytes. 7D is the lower byte and 00 is the higher byte. When this instruction will be executed, current IP value will be pushed on top of the stack. Current IP value is 103, so that will be stored on top of the stack. Then current value of IP, that is 103, will be added with the displacement. In the case of first instruction, displacement is 007D, that will be added with 103, and you will be having new IP, that is 180, and jump will occur. Now we have to execute, we have to see second instruction. We have to discuss second instruction, call 3040. So we are going to calculate displacement for this instruction. So displacement will be 3040 minus 106. So displacement value will be 2F3A. So when this instruction will be stored in memory, first byte will be E8, that is the opcode for near call. Then you have to store displacement. Lower byte for displacement is 3A and higher byte for displacement is 2F. When this instruction will be executed, current IP value will be pushed on the stack, that is 106. So 106 will be pushed on the stack, top of the stack. Then 106 will be added with the displacement, that is 2F3A, and you will be having new value for displacement IP, that is 3040, and jump will occur, or call, you will be calling a subroutine present at 3040 location within code segment. Now we are going to discuss third call instruction present in the table, that is written at offset 106 within code segment, and that is a far call. You are having far label with that call instruction. So call 4500 colon 0430. So before colon you are having new value for CS, and after colon sign you are having new value for IP. Before changing IP and CS, you have to push IP and CS on top of the stack. So first of all, CS will be pushed, then IP will be pushed, then new value for IP will be loaded, that is 430, and new value for CS will be loaded, that is 4500. and that instruction will be occupying 5 bytes in memory. 9 is the opcode for far call, and then you have to store lower byte for IP, that is 30, then high byte for IP, that is 04, then low byte for CS, that is 00, high byte for CS, that is 45. Now we are going to discuss next instruction, that is call AX. That is an indirect type of call instruction that will be of 2 bytes. Opcode is FF, and in second byte you are having D0, that is the machine code for call AX instruction. When this instruction will be executed, current IP value will be pushed on top of the stack. Then you will be loading contents of AX to IP register, and you will be calling a subroutine. Now we have to discuss next instruction, call near pointer within square bracket BX. So here we have to load uh, new value for IP from memory at offset BX within data segment. So before changing IP value, previous value for IP is to be pushed on top of the stack. Then you have to fetch a word from offset BX within data segment, and that word will be stored within in IP register, and you will be calling a subroutine in response. Machine code for this instruction is FF is the opcode for call instruction, and in second byte you are having description for memory, and byte is 17. Now last instruction is call far pointer BP plus 4 within square bracket. So first of all, current values for CS and IP are to be pushed on top of the stack. Then new value for IP is to be loaded from address BP plus 4 within stack segment, and new value for CS is to be loaded from BP plus 6 location within stack segment. Machine code for this instruction will be FF is the opcode, then 5E and 04. So that is the machine code for this instruction. Now we are having return instructions. Return instructions are of two types, as we were having two types of call instruction, near and far. So return instruction will also be of two types, near and far. If you are having a subroutine that is called by a near call, in the end you will be writing a return that will be a near return. So opcode for near return is C3, or otherwise if you have called subroutine by using a far call instruction, then return instruction will also be our far return, and opcode for far return is CB. What is the operation for return? In case of near return, only IP value will be popped from top of the stack. In case of far return, both IP and CS values will be popped from top of the stack. And another format for return instruction is available, return immediate, and operation is the same, that IP and CS will be popped. In case of near return, only IP will be popped. In case of far return, both IP and CS values will be popped from top of the stack. But after that, that immediate number mentioned with RET mnemonic, that will be added to the current value of SP, and SP will be pointing to a new location within memory. Now we are having an example here. Some values are moved in AX, DX, CX and DI registers. Now we have to study effect of call and return instructions on stack. So we have to execute this program step by step. So first instruction is push AX. When push AX is executed, after execution of push instruction, that will be the stack position. SP minus at SP minus 1 location you have stored AX, that is 60 hex, and at SP minus 2 location you have stored 50 hex, that is present in AL. After the execution of push instruction, SP will be decremented by 2. So SP minus 2 is the current value for SP, or top of the stack is at SP minus 2. Now next instruction is push DX. After push DX, stack is shown here. DX will be stored on top of the stack. So higher byte of DX, that is DH, having 5D, will be stored at SP minus 3, and DL will be stored at SP minus 4, and stack pointer will be decremented by 2 after execution of this push instruction. So new stack pointer value is at SP minus 4. Now we have to execute call 130. So that is new position for stack pointer. So IP value is to be stored on top of the stack. The current IP value is 105.0105. So higher byte for IP is stored at 1 SP minus 5, and lower byte for IP is stored at SP minus 6. After execution of call 130, you will be at that location, push CX. After execution of push CX, stack is shown here. So higher byte for CX, that is CH, will be stored at SP minus 7, and CL will be stored at SP minus 8. New stack top is at SP minus 8. Now push DI is executed. That is the state of stack after execution of push DI. Higher byte of DI will be stored at SP minus 9, and lower byte for DI will be stored at SP minus A. Now some program is executed. After that pop DI is executed. So from SP location, DI lower byte for DI is popped. From SP plus 1, higher byte for DI is popped. After execution of pop CX, lower byte of CL is popped from SP plus 2, and higher byte for CX, that is CH, will be retrieved from SP plus 3 location. Then return instruction is present, return 4. So IP will be popped from SP plus 4 and SP plus 5 location, and new stack top should be at SP plus 6 after execution of pop, but as 4 is written with RET instruction, so 4 will be added with SP value. So new stack top will be at SP plus A. Now after execution of return 4 instruction at offset 150, you will be coming back to 107 location. At 105 location, at that is the XOR instruction, and after XOR instruction you will be executing that call instruction, that is underlined. That will be the stack after execution of that call instruction. CS and IP will be stored on top of the stack. You have to store CS first, then IP. So 03 is the higher byte for CS, 40 is the lower byte for CS, and higher byte for IP is 01, and lower byte for IP is 0C. Now you are present at push DX. After push DX, that is the stack top. So DH is stored at SP minus 5, DL is stored at SP minus. Now you have executed the program present within this subroutine. You are now going back to the main routine. So you have to pop DX. So DX is popped from and SP plus 1 locations. Then you have to execute return. That return is a far type return because call is a far type call. So IP will be popped from SP plus 2 location and SP plus 3 location.
and CS will be popped from SP plus 4 and SP plus 5 locations. So that is an example for studying near and far type of call instruction and return instructions.